everyone, my name is David Klee, founder of Sequilibrium. Welcome to Module 4 of my course, the SQL Server on VMware Accelerator. We just wrapped up a good overview of networking and interconnects. This next module covers the physical server portion of this bootcamp. While you may not have the most exposure to the physical server infrastructure, this module is designed to ramp you up on everything you need to know to help you pick out the right equipment for SQL Server workloads and set it up for maximum possible performance. We're going to talk about the types of servers that you're going to encounter, the compute resources inside them, and then we're going to do a deep dive on CPU, memory, and interconnects to help you maximize the performance and availability of these servers. Then I have some guidelines around some specific platform recommendations for some of the more prevalent hardware that I see in the field. Let's get started. In modern data centers, I usually see two different kinds of server hardware topologies. These servers hold our compute resources. The first are just traditional rack mount servers. They can be anywhere from 1U, a small unit of rack space in a server rack, up to 8U or larger, and can contain anywhere from 1 to 32 CPU sockets. The resource expandability in these servers is rather large, depending on the server hardware that you buy. The second are blade servers. Blade servers were meant to run in denser environments, and you can pack more of these in the same amount of physical rack space than rack mount servers. Blade servers are more dense in the same physical rack space footprint, and usually, but not always, hold less compute resources. Blade servers can take a bit more work to manage, as there's usually a management layer for the blade itself and bits to manage on the chassis. I don't really have a preference between the two of these. When managed appropriately, both of these are just fine. I call these out separately because the interconnects that talk to the outside world can be very different between these two architectures, and I'll address those in a little bit. When it comes to physical servers, these contain or connect to what I call the four main food groups. These always contain CPU, processors, and memory. Storage is either locally attached or remotely connected via your interconnects. Networking and interconnect adapters are either physically present in the physical server or virtually connected through your blade server chassis. We're going to talk in detail about each one of these components and how it pertains to SQL Server performance. The compute selection for SQL Server workloads is absolutely vital. We have to make sure that we maintain or improve performance, but minimize your SQL Server licensing liability at the same time. SQL Server licensing is quite expensive, and not buying the right compute components inside your servers could mean you're spending more on licensing than you actually need. We do need to understand our SQL Server workloads fully because many OLTP workloads run very single-threaded, while reporting and decision support workloads can demand a lot of parallel CPU activity. Not buying the right compute or memory amounts also means that your virtual machine density could be lower than you expect, which not only means more SQL Server licensing, but more operating system licensing, virtualization licensing, rack space, power, cooling, cabling, and anything else that comes along with more physical hardware. All of this adds to your capital and operational costs, and that's something we want to minimize whenever possible. We need to balance the amount of memory with the amount of CPU that we need for our workloads and the host density that you're looking for. This is a pretty serious balancing act, and we're going to cover this in detail through the rest of this course. We're going to start with CPUs. Your SQL Server licensing is most likely based off of your CPU core allocations, so let's make sure we set the right foundation. If you open the Task Manager inside Windows, there is a ton of information presented on the screen that might not be readily apparent. First of all, there's a lot of CPU cores here. There's also a CPU make, model, and a rated speed. There's also the actual speed, which may not necessarily line up to the rated speed. There's sockets, logical processors, cache amounts, and the virtualization indicator. Let's dissect what actually goes into the screen and why it matters for your SQL servers. Let's talk about the actual CPU itself. The technical term for the component that goes into the CPU socket on the main board is the CPU package. The CPU package contains one or more processing cores. Each core contains a very small amount of incredibly fast cache memory, in this case level 1 or level 2, which are used to store very low-level operational commands. There's also the last level cache, or level 3, which is shared amongst all of the cores. There's also an area called the uncore, because of marketing, that contains different bits of circuitry that are not directly inside each processing core, but are used to make the package work together. While a lot of information goes in there, the thing that I want you to be most aware of is this memory controller. I'll explain more about that momentarily. If you've ever heard the term hyperthreading, let's explain what it actually is and why it's a bit of a misconception among system administrators. Think of it this way. Every time a CPU executes something, it may have to wait for various external devices, such as memory access time or storage response time, before it can continue to the next command. The CPU is not running at every single clock cycle to execute your commands. What the Intel company came up with a while back is that they extend the unused CPU cycles on your physical CPU cores as if they were a second core. This is called a logical core, and they call the technology that makes this work hyperthreading. Now, there's a lot of additional circuitry inside the chips to make hyperthreading work, but we certainly cannot think of this as a full CPU core that is equally as powerful as a regular core. If you look at the chart here, if a physical core is very lightly used and constantly waiting on external devices, then a logical core may have enough unused CPU cycles to make it powerful enough to help your performance. However, if a logical core barely has any unused CPU cycles at its disposal, then that processing core is nowhere near as powerful as a regular core. It's very difficult to predict this. What a lot of system administrators misunderstand is that these logical cores should never be depended on for full performance to be used by your workloads. As a result, I always tell people to leave hyperthreading enabled and anticipate between a 10 and a 20% performance gain if these cores are used. However, I never want to see them depended on for your SQL Server workloads. We'll talk more about how the virtualization layer impacts hyperthreading in a later module. Currently, there are two main CPU manufacturers in the data center space, Intel and AMD. Intel Xeon CPUs are probably what you're going to find, as AMD has made CPUs that are not really the fastest for SQL Server workloads over the last decades. Recent advancements by AMD, specifically the AMD EPYC CPU lineup, are much faster than they used to be, but I'm still not seeing a lot of these in modern data centers. So while my examples may list the Intel Xeon lineup, I'm certainly not discrediting or discounting AMD for future data center CPUs. If you're interested in AMD CPUs, take the advice over the next 20 or so slides and simply apply them to AMD to verify that those are the right CPUs for you. I want to help you identify the CPUs that you currently have so that you know what you're coming from if you're in the market for new CPUs. In the roughly 2013 era, the Intel Xeon E5 version 2 CPUs were prevalent. These chips were named E5 or E7, then a dash, then a 4-digit number with a version designator after it. Fast forward a couple years, and then the V3 and V4 CPUs were shipped. Keep in mind that while the core counts were increasing and the power savings were improving, the raw compute performance of these CPUs were advancing incrementally. Now, starting in 2018, Intel marketing decided to rename the CPU series. Just to confuse everybody, they called them the Scalable Xeon series. You can tell the generation of these because the second digit is a 1 in their model number. The second generation came out in 2019, and the Intel website has just started to list the version 3 specifications for CPUs that look like they'll be shipping fairly soon at the time of this recording. Just to make marketing matters more confusing, they decided to introduce a classification to each CPU and called it bronze, silver, gold, or platinum, because why not? My personal opinion is that the bronze and silver CPUs are not sufficiently powerful for modern SQL Server workloads. Gold and platinum are where you need to be looking to maximize performance and core count. Gold are generally a little more optimized for speed, and platinum are usually optimized more for core count. If you take a look at some of the more powerful CPUs at the time of this recording, you'll find that these range anywhere from 4 to 28 core CPUs. For example, a good CPU for moderate SQL Server workloads is the Intel Xeon Gold 6244. It has 8 CPU cores rated at a 3.6 GHz base speed and over 24 megabytes of cache memory. I generally don't worry about the thing that they call turbo boost, as it doesn't make that big of a difference for your SQL servers. You can see there's a wide variety of chips out there, and that the scale of these is quite wide. We'll talk more about the individual CPUs and how to select the right one for your workload momentarily. Now, we can't just use osmosis to get a request to these CPUs. These connect to a main board that allows everything to communicate. You'll notice in this image here where this gentleman is holding a main board that contains 2 CPU package sockets. Each socket contains our CPU package that contains a processor with 1 or more CPU cores. Let's take a little deeper look at this main board. This diagram here shows a Supermicro main board that contains 2 CPU packages. Now, this isn't the only thing that matters to us. These black and blue slots immediately next to each CPU socket are for memory. You'll notice that we have quite a bit of them, in this case 8 surrounding each CPU socket. Why do we have architecture split apart like this? Why does this matter to SQL Server? Let's dive in on these. Back in the day, the CPU architecture was relatively straightforward. We had CPUs, and we had memory on the main board. All the CPUs had access to all the memory through the memory controller component inside the North Bridge chip on the main board. This was called a Uniform Memory Access, or UMA, architecture. However, over time, CPU and memory densities started to go up. This memory controller started to become a bottleneck to both performance and upward scalability of the server. The CPU manufacturers developed a different architecture. They decided to put the memory controllers inside each CPU package and then place memory slots as physically close to the CPU socket as possible. This new architecture was called Non-Uniform Memory Access, or NUMA. In this architecture, the memory is located as close to the CPUs as possible. The memory controller is now inside each CPU and runs much faster. Keep in mind that the CPU package 0 in this diagram can access the memory connected to CPU package 1, but it has to work through the other CPU package and its memory controller and back, which can result in a little bit slower memory access. Take a look at this mainboard again. A CPU socket and the memory slots that are very close in proximity are called a NUMA node. This means that the memory is almost directly connected to the CPU socket and makes the memory access time quicker. We're talking nanosecond access time here, and every little bit helps. Like I said a minute ago, this CPU can access the memory on a remote NUMA node, but can result in a bit of a performance penalty. This proximity is exposed through the mainboard to the underlying operating system. If we as programmers can keep our workloads confined to a NUMA node, or at least understand and work with the NUMA node architecture, we can potentially improve the performance and efficiency of that workload. How does this matter for SQL Server? It matters in multiple ways. The primary one is your SQL Server licensing. Your licensing is driven by the number of CPU cores that the SQL Server has available to use. We want to maximize that performance and minimize the core count. First, let's talk about how to properly measure the performance of these CPUs. Gigahertz does not necessarily mean raw performance. There's all the other stuff that we talked about, such as internal memory caches and workload efficiency with NUMA. There's also the core count itself. If your workload is largely single-threaded, more cores probably will not help you, but faster cores in terms of performance certainly can. Other workloads, such as decision support or business intelligence, might actually benefit from more cores. Let's figure out what we need to do to help figure out the right CPUs for you. The big thing that we have to double check with your system administrators is that the CPUs were set up for the maximum possible performance inside the hardware itself. Many of these physical servers will ship with a balanced CPU profile that attempt to save power instead of maintaining high performance. We're already saving power because we're consolidating through virtualization. I have to maintain the performance of these machines. So one little trick that I like to do is to verify if I should disable ACPI C and P states in the physical server firmware. Many times I can measure and sometimes feel an overall performance gain for my SQL Server workloads. Sometimes it is as easy as setting the CPU profile from balanced or OS controlled to high performance or enterprise. Work with your hardware engineers to verify and test your physical server power savings. Let's figure out what's actually in your servers right now. A free utility that I like to use to help to determine the actual CPUs that I have in my SQL servers is CPU-Z. It's available as a free download at the link on the screen, and when executed, will give you the full details on the CPUs themselves. You can see here that I'm running this on my desktop, which contains an Intel Core i9 CPUs with 8 CPU cores and 16 threads, which means hyperthreading is enabled. You can see that the speed rating is quite high, but the current speed when I took this screenshot is a lot higher. You can see the amount of level 1, level 2, and level 3 cache memory present in the CPUs. Keep in mind that if you're running these in a virtual machine right now, the total core count presented to the virtual machine may not be all of the cores present in that physical CPU package. What I like to do is to use this to get the CPU, make, and model, and then jump to the internet to the manufacturer's website to look up the full details on the total cores present. With that information, you now know the number of CPUs that are available to this virtual machine as a whole. Now, this utility does not give us any real indication of actual performance as it relates to my SQL servers. The utility that I like to help understand a more real-world performance metric that I can use to compare individual CPUs with is Geekbench. Geekbench is available at the link on the screen. This utility both has free and paid versions. I'm comfortable recommending this here, as the free version is largely fully featured, with the trade-off that it sends your server's scores to the public site. It sends the computer, make, and model and the results from your test, but nothing identifiable is sent over. It sends this information to their site, but the results are now publicly searchable for you. I absolutely love this because this means that I can research the results from other people around the world to perform relative performance difference comparisons between my CPUs today and the ones that I'm thinking of acquiring. I find that these results provide me the most comparable SQL Server performance expectations over other benchmarking utilities. Geekbench runs a number of CPU tests, not just one synthetic test like many other benchmarks, and this tool provides, in my opinion, the most similar performance comparison to what SQL Server actually delivers. Geekbench version 5 is out at the time of this recording, but it seems like version 4 has more searchable scores for a lot of our server-grade CPUs. The next slide will show version 4 scores, but make sure to review both sets of data so you find the most scores for your particular CPUs that you're looking to compare. Let's take a look at some of the raw results from different CPUs out there. Again, one thing I'd like to point out is that these metrics are from version 4 of the benchmark. Version 5 is out, but since it's a fairly recent release, it does not have nearly the number of CPUs for reference as version 4. Check out both version 4 and 5 as version 5 results will grow over time. You can see a bunch of numbers here for different CPUs that are currently on the market. There is no metric to these numbers, and these numbers are the per core scores. The results also list a number for all cores, but it may not be relevant to us because some of the test beds use virtual machines with less CPUs than were physically present in these VMs. As a result, the multi-core score will be all over the place, whereas a single core score will give us a good idea of the overall relative performance from multiple people's tests. You can see that for a good CPU, the Platinum 8253, the per core score is 3448. The Xeon Gold 6250 has a per core score of 4754. That is a very healthy performance advantage on a per core basis of over 37% faster per core, but at the expense of half the core density of the other chip. If your SQL Server licensing is based on CPU cores, your workload might get this percentage faster if you're not aggressively needing all of the cores in the other chip. You can see some of the CPUs that I personally like to recommend, including the Xeon Gold 6250 and the Platinum 8280. All have per core scores that are very similar. The best part about these numbers is now you have a way to provide a score for a given CPU. You can now have an apples-to-apples comparison with other CPUs that you're interested in upgrading to. You can also do this in the cloud, as different cloud providers do list the CPU makes and models underneath the different virtual machine and service scales in the cloud. It gives you a better idea what to expect for your workload on the new CPUs. Just remember to understand if your workload is mostly single-threaded or parallel in nature. Based on your needs, you can now select the CPU scale that works best for your particular workload. I have fired up CPU-Z on a few machines here. The first we're going to take a look at is a virtual machine in my test lab. Now, the CPUs in the test lab are not really the fastest. It's an older machine, honestly, that I bought refurbished off of eBay, but honestly, it works pretty darn well. If you look, it has an Intel Xeon CPU E5-2670 V3 at 2.3 GHz. Now, this is a two-socket physical machine. Each socket has 12 cores, 2.3 GHz apiece. You can see in the task manager here that I have 8 virtual CPUs assigned to this virtual machine. Let's take a look at a different server. This is a jump box over on a different server environment. You can see this particular host is running an Intel Xeon Gold 5120 CPU at 2.2 GHz. It's only got 2 CPUs on the virtual machine, but again, this will give us enough to be able to figure out the differences in what's actually underneath our virtual CPUs. Now take a look at the CPU on my desktop here. This is running an Intel Core i9-9900K. 3.6 GHz, 8-core turbo boost up to 5 GHz. And you can see right here, core speed are running at about 4,700 MHz on some of the cores. It's doing the recording right now, so it's actually a little bit more active than some of those other machines. This gives us a good enough background to be able to understand what is underneath. What are our CPUs? Now let's take a look at Geekbench so we can see the relative performance differences between these CPUs. We're going to start by running Geekbench on that first virtual machine that's running in my test lab. You can see here this is running Windows Server 2019 Data Center in Geekbench 5. This is still that same Intel Xeon E5-2670 V3. Has 8 virtual CPUs on the virtual machine. You'll notice the amount of memory is 32 gigs, which is accurate, but the designator there, EDO RAM, that's not so accurate. VMware does an interesting job with masking the type of memory that's presented to the virtual machine. EDO hasn't really been a standard since the 90s. So yeah, we're just going to forget about that part. Let's go ahead and run this benchmark and see what we come up with. Okay, we got a result. Now, please keep in mind these numbers are going to look different from the Geekbench 4 version that we've got elsewhere. They changed the scale on here, so they actually look a bit lower than they really are. On this particular machine, we have a single core score of 354. It is what it is. Let's actually compare this with that other machine. Okay, here's Geekbench running on that second jump box with the Intel Xeon Gold 5120 CPU. Now again, only 2 cores on this virtual machine, but let's give this a test. There we go. We have a single core score of almost double the other machine. Not too shabby at all. Now, let's run this on my desktop just to get a comparison between a server-grade CPU and a really fast desktop CPU. Okay, you can see we're back on my desktop, Intel Core i9 9900K, 8 cores, 3.6 gig base, 5 gigahertz turbo boost. Let's go. All right, we got the results. It looks like my desktop is quite literally 4 times as fast per core than the machine that I have in the other room running my test lab. Not too shabby at all. And this is not the fastest chip on the market right now. There's an AMD chip that just cooks anything that Intel can produce, which is awesome. So there you have it. Now you have a really good means to generate a relative number for comparison for different CPUs. So feel free, go take a look at that public database. It's just browser.geekbench.com. You can actually go take these results, look up your current CPU, look up the CPUs of machines that you're looking to buy, or cloud platforms, or wherever, and you can start to get a really good sense. How much faster is my SQL Server expected to run on that platform? Our next IT compute resource is memory. Thankfully, this is a lot more straightforward than the CPU. Since our CPUs drive the work, but our memory is what actually acts as a primary read cache for storage, we want the fastest possible memory speed for our database workloads. Memory speed can vary depending on the type of memory present in the physical machine. Since our SQL Server buffer pool contains all of our working set data, faster is always better here. The unit of measure is RT per second, which means millions of memory transfers per second. Work with your physical server engineers to double check your memory speed and configuration of your memory. On some makes and models of physical servers, your memory may increase or decrease speed based on how the memory is placed in the memory slots on the main board. A simple change to its memory placement could mean a small bump in memory performance. They should be able to verify this for you, and the memory guides that are available from the major hardware manufacturers will help you verify your memory configuration. Here's where the balancing act really comes into play with memory. We'll talk at length about CPU overcommitment in future modules. Some virtual machine admins like to overcommit memory as well. For general purpose workloads, this is not only advantageous, this is a feature. For our SQL Server workloads, however, we simply cannot overcommit memory. Our large footprint SQL Server buffer pools do not allow us to do this. Therefore, we have to balance our CPU overcommitment while maintaining performance with the memory consumption at each host. If we buy physical servers with too little memory, then our memory will be completely used up while our CPUs are functionally idle. This simply wastes SQL Server licensing. If we buy physical servers with what you might consider too much memory, then our CPUs are incredibly active and you have a whole lot of memory left over. Many times this is okay because if a physical server were to fail, we need additional memory to run our workloads on, even if our performance is degraded a little bit. Other times, we'll never be able to address that extra memory, and it could be a waste of money as well. This becomes the balancing act. What do our servers actually consume of CPU? What sort of overcommit ratios can we get with our CPU usage while maintaining performance? How much memory do we need in order to maintain this balance? How can we do this to maximize our licensing? These are all topics that we will address in length over the rest of this course. Our next main IT food group is storage. On some servers, we will have some flavor of locally attached storage for our virtual machines. In most environments, the storage that our virtual machines run on will be some shared external storage device. We still need a little bit of space to install our hypervisor since it is a tiny operating system. Some of these servers actually contain SD card slots on the mainboard. VMware ESXi can natively boot and is fully supported to run off of SD cards or USB sticks. We could also have a couple of local disks in a RAID configuration for redundancy that we install our operating system on. We could also boot directly from the SAN and have no locally attached storage whatsoever. All of these options are perfectly viable and fully supported. However, since just about everything we'll be working on is either going to be shared storage or hyper-converged storage, I'm going to save those discussions for when we start talking about the hypervisor and the virtual machines themselves. Our final component is the network. The physical machines usually contain network interface cards. These can be low speed or high speed. One quick check is to make sure that we have redundancy in our network interface cards. If only a single card is present, that card could have a fault and knock out many of the ports that are on the card. In the larger environments, I prefer to see multiple cards, each with multiple ports, so that we have the absolute most redundancy possible. If you have multiple cards, make sure that the card placement on the main board is on separate backplanes for maximum possible speed. For smaller environments, a single card with multiple ports could provide enough for that organization's risk levels. If you have fiber-connected storage, the same exact rules apply for the HBAs. Multiple cards and/or multiple ports help provide additional redundancy, and putting them on different backplanes on the main board can help maintain performance. If your servers are blade servers, double check to make sure the way these adapters are presented to the blades. The blade enclosure itself may have a different network adapter or HBA topology than what your blade server can see. Related to storage performance, one of the biggest silent bottlenecks that I find today is when your HBA Queue Depths are set far too low for the type of storage that you're using. One big difference between HBAs and network adapters are that the HBAs contain a Queue Depth setting. This Queue Depth setting here is vital to making the most out of fast storage. Think of it this way. My underlying storage could be capable of providing many fast streams of data, especially if it's all flash. If my queue depth inside this adapter is set too low, I may be only sending a small number of concurrent storage requests to the storage itself. It's actually bottlenecked at this adapter and not by the storage. However, if your queue depth is too high and your demand is really high, the storage may not be capable of concurrently handling all of those requests. The default value inside these HBAs is usually a very conservative number so that you don't overwhelm slow storage. These manufacturers do not know what kind of storage you're connecting them to and assume that it's going to be slower than molasses to be safe. If the default value is to not overwhelm slow storage, but your storage is quite fast, the default values can and should be increased according to the type of storage you have connected. Work with your infrastructure team to identify the default values in your adapters and with your storage vendor to understand the recommended queue depth that these adapters should be changed to. Generally, if you're running all-flash or faster shared storage, the default queue depth here is set way too low and could usually be either doubled or quadrupled to make better use of your storage. I recommend that for all-flash or NVMe, you should test this queue depth between a value of 128 and 256. A specific bit of guidance is related to the Cisco UCS Blade Server platform. The default queue depth for their FCOE adapters is 20. This value is far too low for modern storage and is one of the biggest bottlenecks that I see shipped as default values on these server platforms worldwide. Work with your storage teams to change the value at the FC adapter policy for your blade servers to change the LUN queue depth. If you're running other manufacturers like Emulex or QLogic, double check to see what their defaults are for the cards that you have. Most of the time, their defaults are either 32 or 64, which is sufficient for spindle-based storage, but usually suboptimal for flash or flash hybrid systems. Another thing to double check here is with your blade network interconnects if you're using the Cisco UCS platform. Quite fast throughput can result in elevated CPU consumption on the blade itself. By default, the blade will only use one CPU core to process network adapter traffic. One setting I love to change here is to enable receive-side scaling in the Ethernet adapter policy for Cisco UCS. Once I enable this, I need to go into the resource allocation and increase the transmit and receive and completion queue count as well as the receive size for each value. Please refer to the Cisco UCS Network Adapter Tuning Guide at the link on the screen for the specifics for your environment and test accordingly to make sure that you can improve your performance. Woo! Our next module that we'll cover in detail is our hypervisor, VMware ESXi.